Hey guys, wish you a very good evening. Glad you could join in. Quick check, am I audible and is my screen readable? Good evening, Ravi. Awesome. Perfect. 1865. Thank you. Hey, good evening, Arun. Glad you could join in. What's up? Good evening, Satish. Thanks for the OTP. Hey, hi, Sumit. Glad you could join in. How's it going, guys? Welcome to this lecture on named entity recognition. As usual, let's wait for more people to join in and then we can begin. In the meantime, how's everything, guys? Any updates? Rain everywhere just makes me want to sleep. Yeah, I can totally understand. Totally understand. Even so, I'm actually traveling like with my family. Like I'm in Manali right now. So today it actually snowed here, and the temperature right now is very, very low. So I have added layers today. Yeah, but I totally understand. Like when it's really cold outside, makes you just want to curl up inside and sleep, right? Especially in a city like Bangalore. Yeah. With hot chocolate, yeah. Unfortunately, like, yeah, that's not really always available, right? In a city, yes, but in a remote destination, you kind of realize just how privileged we are. Like, not everything is easily available. So here I have to make do with hot water. So, yeah, but it's good. It's really nice being able to travel right now. Hmm, nice. Okay, couple of minutes more, guys, and we will start. Just want to give people a chance to join in. Fewer of us today than usual. Cool. Hot chocolate. Ravi got me dreaming about hot chocolate now. I really wish I had some now. I'll probably see if I can go get some in Manali, like the city, tomorrow. Ah, we'll make one after class. Everyone's united. Perfect. Awesome. I think if I can give you a chance to put on the video, I can just look at it and feel happy. It'll make me really happy. I can get placebo effect of the heat. So yeah, cool. Ah, just a few more seconds and we will start. Awesome. Hey, good evening, Deepak. Glad you could join. I can train. I can train a large language model on my machine for heat. Yeah, that sounds like a plan. I actually have a machine with a GPU on it, so I can just like keep a code running on it and it'll work. Oh yeah, that's a great idea. I can have my own heater in the room. Yeah. Nice. Thanks for the suggestion. I'll actually use it if things get dire. So, anyway, let's start, guys. Today's topic is named entity recognition. We spoke about this problem in the first few classes, like when I was introducing NLP to you, but let's sort of see how it's done using deep learning, right? Okay, so quick recap. Last class, we were talking about this new type of recurrent neural network, which is called a long short term memory, right? Can you guys give me one salient point about this LSTM? on top of the RNN? Like what made it necessary to design this? What is the one advantage that this has over normal RNNs? Can anybody answer that question? Context information, right? Context relevant storage, longer context dependencies. How are we doing it? By introducing a new hidden state, right? We have this new hidden state, which is known as the long-term memory. And using these forget gates, input gates, and output gates, we are able to control what comes into this long-term memory from the short-term memory, okay? So broadly speaking, the long short-term memory is a variant of a recurrent neural network where these different gates help us encode or sort of capture long-range information in this new hidden state. Okay. Quick recap, the forget gate's job is basically to overwrite some information which has been previously encoded over here, right? So the job of this gate is to overwrite some information here. The job of this input gate structure that you see here is to actually do some computation and feed in things into this long-term memory. And the output gate's job is basically to use the hidden state and other information that we have. So right now we're not using this long-term memory to generate our output, but it is possible to do that, right? So essentially what we want to do is to get the output out of this neural network, we use the hidden state and the XT, and this computation allows us to give the output coming out of this recurrent neural network. Okay, so this is like a short recap of the LSTM. Let's go to the agenda for today, right? Today, what we're going to be talking about is the gated recurrent unit. It is an LSTM variant where we don't have this explicit long-term memory state, but it does pretty well by using a variant of these forget input and output gates. So this gated recurrent unit has only two gates, and we will see that they are slightly less effective than LSTMs because they don't have the hidden unit, but they're still pretty competent in the sense that for lesser memory, you are able to do pretty good. You're able to capture quite good relations using this, right? Then we'll discuss a concept which is known as stacked LSTMs. This is a way for us to use multiple LSTMs in a way that we are increasing the overall depth of our network. What is the advantage of increasing depth? If you remember our discussions in computer vision, what does increase in the depth of a neural network mean for us? Yeah. So Arun says more context to store. Sure, that is one way to look at it. But usually when we increase the depth, we increase the representation. Yeah, more non-linearity. We increase the representation power of our neural network. So you could, in principle, if you wanted to take an LSTM and improve its performance, all you have to do is do the stacking. So we will talk about this in detail once we're done with gated recurrent units. Then we're going to look at the LSTM code implementation. I remember, like if you remember last class, we'd seen the outputs of trained LSTM. It was not great, but it was able to do something, right? So today we're going to see how we got that output. So we're going to look at the training of this. And finally, the main topic for today is named entity recognition, right? Named entity recognition is basically a way for you to use NLP techniques to do information retrieval. What's the meaning of information retrieval? Let us say you have a document and your job is to basically get very, very specific information from that document. Like for example, you have a medical paper or you have a certain reviews about medicines, right? What you would want to extract is what is the medicine being talked about? What is the main disease it is trying to cure? What are the side effects of this medicine? And so on, right? So using natural language processing techniques, it's possible to get pointed information from documents, and that is what named entity recognition means. So to be blunt, named entity is nothing but nouns, right? So if you remember our parts of speech tagging class, named entity recognition is going to be nothing but looking at different types of nouns and then categorizing those nouns into different categories. So we'll see a little bit more about this. There are a few approaches that we can follow. We can follow rule-based approaches, conditional random fields, bidirectional LSTMs, and then hybrid approaches, which basically combine these. So essentially what we will do is we will slowly see each of these techniques. And finally, if we get time, we will also look at the code for the NER implementation. Okay, cool. So Arun has some comments. Let me just read that. Yeah, exactly, Arun. So get the company and person's name from list of stock trades like company name, CEO, all that. Yes, yes, absolutely correct. So that is what we're going to do today. Cool. So if we are ready to start, let us start a discussion with what gated recurrent units are. Okay, let's start with gated recurrent units today. Okay. So first of all, guys, in the notebook which has been attached in the last class, right? Uh, this image, the equations over here are actually wrong. Okay. I'll point out why it is wrong, but kind of don't believe this. We will be updating this, right? So finally, when I share a list of uh, a list of different notebooks that we have used in each of these lectures, right? In that, this will be fixed. So I'm really sorry, but we did not notice that these equations were wrong. When I was preparing for today's class, I realized that these are wrong. So what we're going to do is we're going to quickly go and write the correct equations for these gated recurrent units. I'm going to answer a few questions such as what are peepholes, etc. And then we can move on, right? Okay. So let's quickly understand this gated recurrent unit. So first of all, do you guys see that this is also like an RNN? This is also like an RNN. Do you guys agree that this gated recurrent unit is a type of RNN? Okay, so cool. So it is possible. Yeah. So why is this an RNN, right? First of all, because we have these time-dependent states over here, right? We have this time-dependent states over here. Hey, Ravi, my request is put it on the questions tab, right? It will be a bit difficult for me to scroll up and look for this later. So if you put it on the questions tab, it will be easier to find. Cool, awesome. Okay, so essentially, this structure that we see here is an RNN because essentially what happens is this hidden state gets reused, right? So this is essentially an RNN. So now let us look at the types of gates that we have here, right? Broadly speaking, this RNN, right, a gated recurrent unit is divided into reset gates. So this reset gate is going to do the same job that your input and your forget gates were doing in your LSTM. And the update gate that you have here is the output gate equivalent in for this gated recurrent unit. The main change, the main difference between the gated recurrent unit and an LSTM is that now we only have one hidden state. Okay. This hidden state is supposed to do everything. It is supposed to capture long-term information also, short-term information also. And if you look at the number of matrices that we need here, right, it is relatively lower. You need much fewer matrices to do this properly. Okay, cool. So now let us go through this architecture and see how things are flowing through this. All right, let's see how things are flowing through this. So first of all, you have this input x of t, which is coming. Can you guys quickly tell me how do we pre-process our text so that we get this xt? Can you guys quickly remind me? What is it that we do here before we can get this? Yeah, we apply word to vec, right? We apply some neural network which will give an embedding. So at the end of the day, we want embeddings. One way to do it is to use word to vec. Another way is to train it from scratch along with the neural network. Although word to vec embeddings, like using word to vec embeddings, gives you a much better performance boost if you decide to do that. Okay. So we essentially have this. So we have a word which is coming in at time t into this network. The input vector that is there is obtained after using an embedding of this word. Okay. And that is what's going in over here. Okay. Cool. Now let us see where all this xt is going. So this xt first is going here, right? Into this part. So if you notice, there is a product over here along with this xt. Okay. So let's try and understand this diagram a little better. Okay. So what we have over here is we have h of t, which is coming here. There is an element-wise multiplication operation which is sitting here. Okay. And the things which are coming inside this element-wise multiplication operation are this xt is going here. This xt is going through this computational path here, and ht is coming here, right? All of these things are going into this. So if we had to write the equation here, there are multiple ways to do this now. Okay. One way is to actually apply some processing on this ht as well, right? So typically in a gated recurrent unit, you will have this matrix ur over here. Okay. So what happens is you have this hidden state from the previous state coming into this element wise multiplication as follows, right? So first let us identify what is this RT, okay? So this RT is nothing but this X coming here, passing through this linear, this dense unit like thing. So this is like a matrix multiplication with a bias. This goes through a sigmoid and that gives us RT, right? So first let's write the equation for this. RT is nothing but sigmoid of WR, right? WR, which is this matrix. This is like a dense layer. WR into XT. Okay, this is what's important. It's WR into XT plus BR, right? This is the bias associated with this operation. So we are doing this to get our RT. Okay, we are doing this to get our RT. Now, once we have our RT, RT is going to give us a vector which is of the same size as our h of t, right? Same size as our h of t. So what we're going to have here, so kind of just one moment. I think I made a mistake before. This is not taking x and sending it there. The contribution of x is going to be this, right? So what we're going to have now over here. Okay. The output of this is going somewhere. Right. So both of these arrows are coming here. The output arrow is coming out like this, right? That is what this means. Okay. So let's do it properly now. So I have my xt which is coming in here. It's getting multiplied by this WR, this sigmoid, and this thing to give us RT. This is now going to get element wise multiplied by HT. And we optionally have we have an option now of using UR. Okay. So now we have two ways of doing this. So let me call this output as OT over here. Output at time t. OT now is going to be our HT minus 1. Okay. So we have two options. Let me list out both of them. Okay. We have HT minus 1 element wise multiplied by. So this is element wise multiplication. So let me just make a note of this. If I'm putting a circle around the multiplication sign, this is element wise multiplication. Right? Okay. So I have HT minus 1 element wise multiplied with RT, and that is what my OT is now. Or this could be not W, the matrices with HTR UT. So you have UR over here multiplied by HT minus 1 plus this BR. So let me write it as BR something else. So let me write it as BRR actually. Yeah, just to separate it from this one here, right? Okay. So I have this element wise multiplied with RT. So I have two options. Depending on whether I want to do some processing on my hidden state or not, I can have these two options here. Okay, both are valid and both variants are there in the literature. Okay. So once we have this, what you have to notice here is this OT is going over here, right? If you notice this path, it's going and sitting over there. So let's do that a little later. First, let's focus on this path now. Okay. So I have my xt which is coming here. It is passing through this matrix over here, wz, right? So this operation, xt multiplied by wz, and the sigmoid over that, the output of this operation is going to be zt. So let's write the equation for zt. Okay. So now my zt is going to be wz times x t plus bz. Okay, it's going to be this sigmoid of this. This is going to be my zt. Now, interestingly, something fun is happening with this zt, right? Zt is now splitting into two parts over here. The first part goes into this minus 1. Okay, the first part goes and multiplies with this minus 1, and then is element wise multiplied with this ht minus 1. So let's trace this part. Okay, let's write the equation for this part. Let me quickly make some space here. I'll just make this a little smaller. Yeah. Right. Sorry, one moment. Cool. Yeah. And let's write the equation for this. Ajay says this is not -1, this is 1 minus. Okay, hold on. Let me check this once. Am I taking my ZT and doing 1 minus this? I am doing 1 minus this, yes. Because this is going to be 1 minus this part, element wise multiplied by this, followed by this part, element wise multiplied. Yes, you're right, Ajay. Thanks for that. Thanks for pointing that out. This is not going to be negative. Although just one moment. Let me, confirm this. This is 1 minus ZT over here. Okay, cool. So I now have my HT minus 1, which is following this path, right? I have my HT minus 1, which is following this path. It's getting element wise multiplied by 1 minus ZT. So let's write that part now. So I'll call this my YT, let us say. Okay. I'm going to write YT as HT minus 1. Okay. Element wise multiplied with 1 minus ZT. Okay. And this is what I get at this point, right? YT. Now let us follow this path over here. So this path, HT tilde, let's come to this point over here. So HT tilde is nothing but WH times XT, right? It's WH times XT plus BH, the whole passed through a tan H, a hyperbolic tangent over here. So I have my tan H sitting over there. This is my HT tilde. And finally, to get HT over here, let us see how we get HT. Okay. So HT now is going to be YT plus HT into ZT, element wise multiplied by ZT, right? So this is nothing but 1 minus ZT multiplied by HT minus 1, right? Yeah, plus HT minus 1 element wise multiplied by ZT, right? Just one moment. Let's check if this is correct. Yeah. Okay, the last one is HT, right? Okay. Hold on. Just one moment. I'll just quickly write this part again. Okay. Indradeep says, is it not getting concatenated with HT tilde, with XT and HT tilde? Just let me check that. So I have my HT minus 1 coming here. Is this getting element wise? Is this getting merged? So my understanding is when you decide to merge that, right, it is the peephole version of that, right? It's the peephole version of that. Right. What I have is OT over here. Got it. So my OT is coming here and getting multiplied with this. I got it. Got the problem over here. Just one moment. Let's update this just one more time. Oh, sorry, that was not wrong. HT tilde, this was wrong, right? This is not XT, this is OT. Correct? This is OT over here. It's OT that is coming and sitting here. And finally, we have this thing, right? HT tilde multiplied by ZT, element wise multiplied by ZT. And this simplifies to HT element wise multiplied by 1 minus ZT plus HT tilde element wise multiplied by ZT. And this gives us the correct set of equations for this model, right? Okay. So broadly speaking, these equations are the correct ones for the gated recurrent unit that we have here. So HT minus 1, where? HT minus 1 into 1 minus ZT. Right. My bad. There's a T minus 1 in the this thing there. Yeah, thanks for that. HT minus 1 element wise multiplied with 1 minus ZT plus HT tilde element wise multiplied with ZT. Yes. So Deepit, yes, for this concatenation thing, right? My understanding is if you decide to use peephole connections, right? So the whole point of a peephole connection is that you start concatenating your hidden state with your xt every operation. So if I go through these equations and everywhere I see an xt, if I replace it with this term over here, right, ht minus 1 comma xt, then it goes and becomes a peephole connection. Let me quickly check if there is any concatenation between xt and ot. Is there a concatenation? Yes, there is a concatenation happening here, right? That's correct. So this is where xt and ot are getting concatenated. And then it's passed through this. Yes, my bad. I'll quickly update that. Okay. So essentially, this is what I will have for my gated recurrent unit. Now, if I wanted to include peephole connections, right? A peephole connection is nothing but wherever you're doing your computations, you take a look or you take a peep at the current state of the memory, right? So if I now go and replace all xt with xt comma ht minus 1, right, with this. So guys, do you understand this? This means I'm basically concatenating these two, right? Deepak, that is what I'm explaining right now. What I mean by a peephole connection is wherever I'm doing some computation on the input, right? Wherever I'm doing some computation for this thing, wherever I'm doing some computation on my input word or my input embedding, if I simply replace all of that with a concatenated version between xt and ht minus 1, right? The memory and the input, if I just concatenate them, that step is known as peephole connection. Okay. So we can actually have peephole connections even in our LSTMs. So if you remember the LSTM equations that we saw last class, right? Let's quickly see them. The LSTM equations that we saw last class, we saw that there was some concatenation happening here, right? Now, additionally, if we take this long-term memory over here and also concatenate it here, right? That is known as a peephole connection for LSTMs. For the gated recurrent unit, the peephole connection becomes wherever I have xt, I'm replacing it with xt comma ht minus 1. That becomes a peephole connection. Okay. So that is what we mean by gated recurrent units with peephole connections. Simply everywhere I see an xt in these equations, if I replace it with this concatenation, then we get GRUs with peephole connections. Cool. Okay. So I'm going to pause here, guys. This is how we interpret the computation diagram of a gated recurrent unit. If anyone has any doubts at this point, please point it out. By the way, did I get the equations correct? Did you guys, or do you guys spot anything which I have left unchanged? Can you please highlight that? Okay. Arun's question is advantage or objective of peephole in reality. So Arun, it's like it gives you additional computation. So see, usually when you are doing a computation, right? In general, in deep learning, what we try to do is we try to give as much information to that operation as possible. So a lot of times, a simple way to improve performance is simply to make sure all your recurrent connections are seeing both the input and the hidden state at some point, right? So in the papers which discovered this, they reported a slightly higher performance than GRUs without peepholes. The reason for this was that I'm not just including my current word in my computation. I'm including the hidden state as well as my current word in my computation. Okay, I'll repeat the peephole concept once more. So the concept of peepholes was discovered by people who thought that we can improve the performance of an RNN simply by giving every computation within the RNN access to the hidden state as well. Okay. So whatever equations that you have. So for example, first let's talk about peephole connections for LSTMs. In LSTMs, the way for me to introduce peephole connections is to add connections between this long-term memory and everything that we see here, right? So if I simply go now And in all my equations, wherever I see ht minus 1 comma xt, I replace it with ht minus 1 comma xt comma ct minus 1. If I simply do this, it is like a peephole connection. Why? Because it is giving access for this dense layer. This dense layer now is not only seeing my short-term memory and my word, it is also taking into account what the long-term memory is. So it is a way to add more context information. Is this high level view clear to everyone? Is the high level view clear to everyone? Okay, two people. I hope others are also clear with this. So the whole point of peephole connections is to give every computation here access to the memory over here. Okay, so this is how we implement peepholes in LSTMs. Wherever we see ht minus 1 comma xt, simply add or concatenate the ct minus 1 there, and you have LSTMs with peepholes. Okay, if you guys don't believe me, you can check this out on Wikipedia. Like the Wikipedia article explains this really nicely, so you can check it there. Then in a gated recurrent unit, the way for you to introduce peepholes is to, wherever you see xt, right? Wherever you see xt, that is just your input, you replace it with now a concatenation of ht minus 1, which is the memory or the hidden state, with concatenated with your input, right? So that is the concept of peephole connections. Cool. Are we clear now on how peepholes are implemented for GRUs and LSTMs? Okay, awesome. So if you guys are wondering why this was done, it showed slightly improved performance, although I won't believe the reason that the paper claimed. Okay, the paper claimed that this is because we're giving additional contextual information. All that is fine, but computationally speaking, it doesn't make any mathematical sense to me. Honestly, it's like one of those those intuitive tricks that you try which worked out well. It's like one of those discoveries. I wouldn't really associate it with any meaning as such, but yeah, that is how it came out, right? Okay. Now, guys, there is one more way of doing this. Wherever you see ht minus 1, right, you can again replace that with some more computation. So if you keep adding dense layers in each of these, right, you will get different variants of these gated recurrent units. And there is this amazing paper, review paper in 2015. I'll just show you the link to it. The link is available in today's, in either today's or last time's notebook. Let me just check, right? Oh no, not here. It's not there in today's book. Just one moment. I'll quickly check if it's here. There is this review paper which talks about, okay, it's not here. I'll quickly add that paper. Review of RNNs. Critical review. This one. This paper talks about how most of these RNN architectures, right, they will only have delta changes in performance. So although there are so many variants of them, right, although there are so many variants of gated recurrent units, LSTMs, and so on, most of these recurrent neural networks have performances which are in a range. Okay. And if you really want to improve upon them, you will have to go for more complicated computations such as attention, which is what we'll study next class, right? So if you guys have time and if you're interested, you can go through this. Paper. Okay, I'll just attach it over here, and I will also include it in today's notebook for completeness, right? Just one moment. RNN review paper. So this is an excellent read if you have time. What this paper does is it collects a lot of work in RNNs and it compares the different types of strategies which are effective. And the conclusion of the paper is most of these modern or old RNN architectures, the performance is not really that much. Like the performance difference, even with all these variants, isn't that much. If you really want to do better, then you have to go for a different computation mechanism. So just wanted to point that out. Cool. So if you're stressed about having to remember all these variants, you don't have to, because there is no extra gain by remembering them. The performance you can expect is within a certain range, right? Okay. So this completes our discussion on gated recurrent units. Now let's talk about an important concept which is known as stacking of LSTMs. Okay. So RNNs on their own aren't that good, right? Because they have very, very limited amount of computation by which they have to get everything done, right? So one cheap way of increasing the representation power of your LSTM is to do the following. So first of all, this idea of stacking LSTMs applies to all RNNs in general, right? So let me now draw a diagram where I have an RNN sitting over here. Okay. Can you guys quickly tell me what are the inputs to this RNN? What goes into this RNN? My embedding, XT. Can I say an XT goes into this? This is the embedded vector. Another input that this RNN takes is this HT minus 1, correct? The output of this is HT. And then we have another OT over here, right? We have another OT over here. Now, the idea behind stacking RNNs is very, very simple. Okay, it's very simple. All it tells you to do is you make a copy of this. Okay, you simply put a copy over here. Okay, and now the output of this RNN, right? The output of this RNN goes and feeds into another RNN as the input to that RNN, right? So all we have to do is we have to take this output from this RNN, feed it to this RNN. Everything else remains the same here. My HT minus 1, HT, everything remains the same. All I have to do is now chain these together. Okay. And this is like a very general way of doing it. We can apply this idea to gated recurrent units. We can apply this idea to LSTMs. We can apply it to the RNNs we studied 2 classes back. All of them, same concept. The outputs that this is generating goes and sits into another RNN. That's all. So maybe if we do this a few times, right? If we do this a few times, eventually we will get this over here. And this will be our final output. Final output. Okay. Now to separate these, let me also add these. So that let me call this of 2. Let me call this of 1. And let me call this after K such steps. Right? Okay. So Arun's question is, where will my second word come into play? It will come into play here, Arun. Right? So let us say I'm encoding the word the right now. Okay. So now the will feed into this. It will generate an output over here, which is associated with just this word the. Okay. Let us say the word the appears at time step, say 3. Okay. Let us say this is occurring at time step 3. For time step 3, this will generate output, which is at time step 3, right? Now this output will go and feed into this RNN. This output will also be for time step 3. This output will also be for time step 3. Finally, the final output that we're getting will also be for time step 3, right? So now I will keep repeating this per time step. Every time I take one step over here, I will take one step in all the chained RNNs as well, right? I will take one step in all the chained RNNs. So do you now see how they can be this thing? Do you now see how they're coming into play, Arun? This makes sense, right? So at time step t, you simply propagate it throughout the depth of the network, and the next step will be done through repeating the same thing. Okay. So Indradeep's question is, so OT from RNN1 is input to RNN2 at time t plus 1? No, not at time t plus 1. At time t only, Indradeep. That's the point, right? We don't want to take one further step here. The time step of all my RNNs will be synchronized, right? I will synchronize all the time steps over there. So this is like a batch update for HT minus 1. Like same HT minus 1 for all vertical levels. No. I will have different HT minus 1s, right? See, the whole point is this. I have, let us say, 3 matrices in this equation for this RNN. Then I will have 3 more over here. Then I will have 3 more for the next one. So the way I'm increasing my computational power, or the way I'm increasing my representation power over here, is by allowing more trainable matrices to come into play, right? These more trainable matrices will now take a lot of contextual information into account and then go forward, right? So whatever is missed by my first RNN will be picked up by my second RNN and so on, like that. Okay. So ht minus 1, what you have to remember is different. So I will have one different hidden state over here, different hidden state over here, different one here, right? So let me also put that down. This is say of 1, this is of 2, and this is of k, right? If I have k depths. ht minus 1, not ht. So ht minus 1, Arun, I will just initialize it to this thing, right? I will just initialize all of them to 0, and I will keep doing this, right? So the first time I will use this thing, it's very, very likely that all these RNNs will give you different HT plus ones, right? They will give you different HT plus ones. So that is why more often than not, you will see different hidden states throughout. Okay, you will see different hidden states throughout. Okay, perfect. So now let us now apply this concept of stacking LSTMs to solve the problem that we had done last class, right? So quick recap of the problem we were trying to solve last class. Last class, we were trying to replicate what InShorts does. The problem that we were trying to solve was that of text summarization, right? So given a newspaper article, our job is to generate the headlines for that, okay? So what we will do now is we will use an encoder decoder architecture to essentially do this task. What is an encoder decoder architecture? It is something like this. So I have an encoder which is sitting over here. This encoder is basically just going to see the article. Okay. The final encoder hidden state is going to be passed to my decoder. The decoder is not going to see all the hidden states of the encoder. Okay, that is important to remember. The decoder is only going to see the final encoder hidden state. Based on this final encoder hidden state, it is going to generate all the outputs. Okay, so the decoder's job is to give you a sequence which will give you the headline. The encoder's job is to read the article, make sense of it, and transfer that information through this encoder hidden state. Okay, so now let us see how to implement this kind of an architecture using stacked LSTMs using Keras. Okay, let's do that. Cool. So let's quickly run through this code now. So as usual, what I will need to implement from Keras to do this is from tensorflow.keras.layers. The most important thing for me here is this LSTM. Okay, this LSTM is most important for me. Another thing that I'm going to be using is this time distributed class. Yes. So Indradeep's question is, so a decoder only gets activated after encoder has seen all the article? Yes. Yes, Indradeep. Decoder only gets activated after the encoder has seen the article. Cool. So this time distributed class over here, the job of this time distributed class is to add a hidden layer which will be applied to different time outputs. Okay. So if I just add a dense layer to my RNN, it will take all the outputs of my RNN and then apply a dense on it. But if I pass my dense layer first through this time distributed, it will make sure that it will apply the dense layer once per output. Okay, that's the difference between a normal dense layer and this time distributed dense layer. Okay, so now let us quickly see how we're going to do this. First, we have to do our usual text pre-processing, right? Our first task is always to clean our text so that it can be tokenized and used in a logical way. So let us see all the steps that we're doing here. We're essentially removing all the tabs, the character returns, right? We're basically getting rid of all the special characters which add new lines here. Then we're going to get rid of a dash, right? So if you have this dash occurring in your text, it's going to remove that. This is going to remove all the full stops. This is going to remove all the special characters. This is going to remove all these double quotes. So this \x9* is basically Unicode for the double quotes character. So this will get rid of that. Then we have, yes. So then we will remove some commonly occurring patterns over here, and we're going to make it CM num for some reason. Okay, so that's one thing which we're going to do. I guess this is dataset specific, and it becomes important to do this. And finally, we're going to remove punctuations at the end of the word, right? So basically things like comma, full stop, things which get attached to a word, that gets removed here. And this finally is going to remove all the spaces. So after this pre-processing pipeline, we get our clean text, right? So we now have our clean text, which basically looks like this. We apply the same thing to our summary column as well, right? So we have the summary, which has been generated by humans. We have the text, we have the clean text over here, and the clean summary. So we'll apply this pre-processing pipeline to both. Once we do that, we are going to essentially get rid of all the entries, all the rows which don't follow our original decision, right? We want this to be between 40 and 60 words in length. So we're going to apply that. Once we're done with that, we are left with 47,500 examples. Okay. So now we're going to use just these 47,500 training examples to train our LSTM. So now let us see how we are doing this part. Okay. So let's sort of move on here. These steps are nothing but getting all the rare words. Rare words are defined as those words which occur less than 5 times over here, right? So in our for us, the threshold is 5 words, and this function is basically going to get all the rare words. Let's see where to use that. Then we're also going to tokenize our data set. Do you guys remember what tokenization is? Okay. Tokenization. Okay. So quick reminder, tokenization is nothing but taking all the words, giving them some index numbers, right? That's what tokenization is. Okay. So that happens over here. One thing that we have to sort of get access to, right, is we have to prepare these. Okay, that's not done here. That's going to be done later on. Okay. Let me talk about it when we get there. One thing that we are going to do is we are going to pad our sequences with zeros up to the maximum length. Okay. Guys, we kind of talked about this a couple of classes back, right? When I was talking about RNNs. I just want to see if you guys remember this. An RNN can take variable length inputs, right? But then why am I sitting and padding the sequence here with zeros? What's the need for this? What's the need for this? My RNN inherently is able to take any length of words as input, right? But before I'm training my network, I'm actually doing this pad sequence operation. If I have a sentence of length 40 characters, if I have an article of length 40 words, I'm actually sitting and padding it till it becomes 60 words with zero. Can anybody guess why this is? I'll give you a hint. We talked about this when we were looking at the vanishing and the exploding gradients problem. Can anybody give me an answer? Why is it important to pad this? Anyone? Same length? Yes, we want to bring it to the same length. Why? Stacking it so the input needs to be of correct format. If some embeddings go to zero, then won't flow through the deep network. Sure, yes, I agree. But what is the side effect? What is the side effect if we don't pad this? So let me tell you, it has got nothing to do with the code. Okay. If you're thinking this is because my neural network will only take fixed length inputs, it's got nothing to do with that. Yeah. Although I have variable length inputs, I'm padding it. Why? Come on, guys. It's easy to guess. Can you guess it? The issue is with the gradient updates. Can you guys tell me what happens if I raise a small number to the power 40 versus I raise it to power 60? Which one will be guaranteed to be smaller? Let us take 0.5. Okay. I will raise 0.5 to 40. I will raise 0.5 to 60. 0.5 raised to 60 will be smaller than 0.5 raised to 40, right? Yeah. So that means my gradients for long sentences is always going to be smaller than my gradients for short sentences, right? My gradients for long sentences will always be greater than my gradients for short sentences. So my model will automatically favor small sentences as opposed to long sentences. So this is one very important reason why we need to zero pad our input sentences so that we don't get any unnecessary bias because of the lengths. Okay, this is the main reason we do it. It's got nothing to do with the code. It's got nothing to do with other stuff, right? The major problem here is we don't want any unnecessary bias to short sentences, okay, while we're doing gradient updates. So that is why we're going to sit and pad these. Once we've padded these, let us now actually implement our encoder decoder architecture, okay? So I want you guys to see something here. First of all, I have my latent dim, my embedding dimension, my max text length, and my max summary length, right? These are things which are coming from our configuration, which we had seen last class. If you remember correctly, max text length is 60, max summary length is 30, embedding dimension was 200, I believe. Latent dimension was 300, something like that. Let's quickly go back up and see this in our config. Yeah, 300 and 200, right? Embedding is 200, latent is 300. We have 30 and we have 60. Okay. So these are our numbers. Let's go and see what we're going to do with this. So the first thing I'm going to do is define the encoder inputs, right? This is nothing but an input layer of shape max text length. So this is what's fixing the length of the inputs for us. We have this embedding layer, which is going to take my X and it's going to go through that, right? This is the embedding. So I'm basically deciding to train my embedding along with my RNN. Then I have encoder LSTM1, encoder LSTM2, and encoding LSTM3. Why do I have 3 encoder LSTMs? What am I doing here? We just saw this. What am I doing here? I am stacking them. Perfect. So I'm stacking these so that I improve performance. Okay. So let us see how we're stacking. This is kind of important. So what you have to understand when you're stacking things using Keras, right? You have to give this return sequences to true. Okay. If you give return sequences to true, it is going to not just give you one output, but all the outputs in your 60 inputs. For all your 60 input, it's going to give you 60 outputs. If you make this return sequences equal to true. So I have to do this for encoder 1. I have to do this for encoder 2. I'm doing it for encoder 3 also. Okay. And once I give this as true, right, I have to take the output of these sequences in the first thing that is coming here. So this encoder output 2 is the one which is going to have all 60 outputs from all 60 layers. Can you guys quickly tell me in the LSTM, is my output and my hidden state different? Yes or no? Output and hidden state is different in an LSTM. True or false? It's false, guys. It's false. In an LSTM, if you remember the architecture, right, whatever output I'm getting is the same as the hidden state, right? Sorry, 1 minute. Yeah. Whatever output I'm getting is same as the hidden state. So I got a 50-50 answer. The answer is yes, the hidden state and the output is going to be the same for an LSTM. Okay. So essentially now what I have here, after I implement this, I have all the 60 outputs of all the 60 hidden states generated over here. The final hidden state is over here, and the final long-term memory state is over here. Okay, that is what I'm getting from my encoder LSTM1. Then I'm getting the same from my encoder LSTM2. If you notice, I'm simply passing encoder output 1 through this, right? Because there are 60 things generated here, those I'm passing as it is to encoder LSTM2. And then the same output of LSTM2 I'm passing as it is to LSTM3. Okay, so this is how I achieve stacking in code. Okay, cool. So once I've done all this, I'm going to put a single decoder now. I don't want to have much, I don't want to sort of experiment too much with my decoder. I'm going to just have a single decoder layer. So decoder layer is also going to have an embedding. Then the decoder LSTM is our usual LSTM. We are going to say return state and return sequences to true. So we are going to get all the outputs over here, right? So Arun's question is, hey, I disagree. It depends on the application, right? Many to one. So in a many to one, how will you stack your LSTM, right? Arun, I think in a many to one, the stacking will be the same. Output is hidden in many to one. No. Arun, for RNNs, the output and the hidden layer are different, right? For an LSTM architecture, by nature of the architecture itself, see this, by nature of the architecture itself, whatever HTM generating is taken as the output over here, generally. So yeah, this is by nature of the architecture. It's not this thing. So, okay, cool. Coming back, we now have this kind of an architecture. Sorry, wait, where did we go? Let me go back to our code here. This is what we were discussing. So now I have my decoder LSTM. From this decoder LSTM, I'm essentially taking all of these. Why is it necessary to take all? Because I now want to do many to many, right? This is a many to many kind of thing. I want to get all outputs. All the outputs will be basically a word, and that word is going to be my summary. Okay, cool. So what is recurrent dropout in the code? Let me check. Where do you see this? Decoder, okay. Oh, dropout here, recurrent dropout, okay. So recurrent dropout, I believe, will be, okay. Recurrent dropout is actually set for all of them. I believe it's a dropout layer put after your final hidden state. So the dropout over here will be applied to all the matrix operations. Recurrent dropout, my guess is that it is the dropout from after the hidden state. Let's confirm this, right? Keres, working with RNNs. Let's go here and let's see the LSTM, right? Yeah. Fraction of the units to drop for the linear transformation of the recurrent state as opposed to dropout. Fraction of units to draw linear transformation of the inputs. Okay. So I see. So you have some matrices associated with your hidden state. You have some matrices associated with your normal input states, right? So we have both types of matrices. So in the LSTM, if you're applying a dropout only on these things, right, which are being applied to the input, then it is this dropout. Otherwise, it is the other dropout. So I guess it controls the dropout on which of these matrices it's applying on. Cool? Indradeep? Cool. Okay. Now let us so finally this is the model that we have. Okay. We have these encoder inputs and decoder inputs, and the output that we're taking from this is the decoder inputs. Okay. Once we have run this code cell, this is what our architecture looks like. We have three LSTM layers and one single LSTM for my output. So once we compile and train this model, so we essentially trained this model for 500 epochs, but with early stopping, it actually turned out to train only for 90 epochs due to early stopping. And once we plot this is what the plot looks like. Can you guys quickly tell me, is this overfitting or underfitting? This kind of thing? Train and test loss, overfitting, right? So this is somehow kind of better for my training set rather than my test set. So we are overfitting here. Let's just be aware of that. Okay. Now comes the most important part. We now have to actually reverse encode the index to their tokens. So when we were creating this tokenizer, right? Basically what this tokenizer does is it takes a word, it associates an index with it, and it sends that one hot encoded vector as input, right, to your embedding layer. So now what we have to do is when we are getting outputs, we have to reverse engineer what word it meant based on the number which is getting, right? Okay. So what was the embedding layer before decoder? Does it create embedding output? Okay, let's check that. So, okay, let me explain this. The embedding layer after, so see this, okay? Once we have taken this HT, right, you might want to add one more embedding layer here, right, before we get the final thing. So we will have one matrix operation which is basically taking the hidden state and generating an embedding after that. So that is what the embedding after the output is. I'll quickly show you this in the code. So my decoder embedding is this one. It is basically applying this embedding to the decoder inputs, right? So the decoder inputs are nothing but these. Yeah, so decoder inputs is basically a single thing over here. So 1 minute. Yeah, so decoding embedding layer is this. So embedding of y walk, embedding dimensions trainable true, and we are basically taking the decoder inputs. So the Okay. So my bad. This is not here. The embedding that we're talking about here is not this. It's actually an embedding layer being applied between my encoder and decoder. So the decoder embedding is this one over here. Just one moment. If I come back to my encoder decoder architecture, where did that go? Okay, I just need to look for that. Architecture, just give me 1 second, please. Where did that go? Yeah, this one. So essentially, there is an embedding layer present here. So before my final state is fed into this decoder, we have this over here, Deepak. Does that answer your question? Indradeep and Deepak? Guys? Is it word to vec? No. It's the embedding layer, right? It is, yeah, it has the same structure as a word to vec. It has the same structure as a word to vec. Right? Okay, cool. It's not word to vec. It's not pre-trained word to vec. It's got the same structure. Indradeep's question is it embedding what? The HT? Yes, Indradeep. We're applying some computation before we pass the hidden state to the decoder. So it's like this, okay? In general, in deep learning, if something is not working, add more computation, see if that solves the problem. So it's that thing happening here. So yeah. Okay, cool. So now finally, guys, let us just quickly discuss this, the decoder inference architecture. Once we discuss this, we'll be done with our LSTMs, right? Okay. In Bishwarup's question is, do these things run on simple collab? Yes, Bishwarup. We wrote this code. We used only 3 LSTMs because that is what would fit in the free version of this. So we have, yeah, we do need GPU, but a free GPU will be okay. A free GPU is good enough to run this code. If you notice, it takes about 1.5 hours. So there are 90 epochs. Each epoch takes about a minute. So this entire training took 1.5 hours. 1.5 hours is what you can expect to get out of a free GPU. So you can do this Google Colab free. Okay, you can use the free version of Google Colab to run this. Okay, so coming back, we now have the decoder outputs, right? The decoder output at each stage is what I now have to process to get the final output out of my model. Okay, so for this, it becomes important to get the reverse index of my tokenizer, right? So reverse source word index, reverse target word index, these are nothing but inverse mappings from number to word. Okay, so just remember that. We are now going to use this inside this decode sequence function. So whatever output I'm basically getting from my decoder model, right? Output tokens. This is now first passed through an argmax operation. Why? Because if you remember, we were using categorical cross entropy. So the predicted word is going to be the argmax version of the output tokens over here. Once we have the word which had the maximum prediction, we will apply this reverse target word index on this to get our sample token. To get the final word, we actually need to apply this reverse mapping. We keep doing this in a loop for all the decoded outputs. So let's take a look at the stop condition. Okay, so this decoder will stop going in the following case. If sample token is equal to EOS stock. So if my predicted word is this EOS stock, what is EOS stock? It is the end of sentence token. Okay, it is a junk word that we created for the purpose of training. If the sample token is this, or the length of the decoded sentence is greater than my max summary length, then I will stop generating. Okay, otherwise I will keep running this. And that is how I will get the prediction from this. Okay, so if you are interested, you can go through the details of this to understand exactly how to do this. But after we do all of this, we will get our prediction summary, right? So our predicted summary is going to be decode sequence of the outputs of this model. It's going to be the decode sequence applied to the outputs of this model, and that is how we get all of these predictions. Like we saw last time, these predictions aren't great, right? We saw that some of them are really, really funny, and one way, like one of the issues with our training is the following, okay, guys? One of the issues with our training is that our training loss values look kind of small, right? Our accuracy also looks really large. If you notice here, this is 79% accuracy versus 74% accuracy. Don't you think, looking at these numbers, that we should have gotten pretty good accuracy? Shouldn't these numbers tell you that, oh, my model trained really well? But here is the issue. Here is the issue. The accuracy is counting. The accuracy that we're measuring here, right, is looking at the prediction accuracy. Okay, it is looking at how close is my output vector, the one hot encoded vector. How accurate is it in those terms, right? That is not the accuracy that we should be looking at. The correct way to judge whether a summary is good or not is done through this method, which is known as recall oriented understudy for gisting evaluation. This is known as the Rouge score. So yeah, so here this accuracy numbers don't mean anything. If we really want to judge how well our model is doing, we have to go for these Rouge scores. Okay, so Rouge here stands for recall oriented understudy for gisting evaluation. So let us quickly just understand this Rouge score a little better. Rouge score is very straightforward. It is nothing but unigram, bigram, trigram. Okay, Arun is asking me to repeat this part. Arun, how about I explain what this is and then we'll go back? Yeah, okay. So my Rouge scores are essentially a way for me to evaluate the quality of my summary. Why do I need a new method to evaluate the quality of my summary? Because when I'm training, right, when I'm training my model, I have an accuracy over here, right? This accuracy that is being computed is simply looking at the bag of words when it's calculating the accuracy, right? If the word which is there in my original in my actual summary and the word which is there in my predicted summary, if these bag of words match, my accuracy will be pretty high. But just having a bag of word matching is not good enough. We need to actually pay attention to the order in which these things are coming. Right, Arun? Right? Do you agree? We have to pay attention to the order. Okay. So now my Rouge score is a way for me to evaluate a metric which takes equal account onto the order of the thing as well as the meaning of the summary. How is it doing that? So essentially, Rouge scores come in many forms. So you have Rouge 1, Rouge 2, Rouge L. So let us go and see what each of these are, right? Just one moment. I want the Wikipedia article. Yeah. Right? Yeah. So essentially, my Rouge N is basically going to look at the overlap of N grams between the system and reference summaries, right? So Rouge 1 refers to the overlap of unigrams between the system and reference summaries. It is not going to treat my predicted and my actual summaries as bag of words. It is going to treat them, it is going to see the positional information, right? It's going to see the positional way of looking at these. So essentially look at this, French, right? So the fact that this French and this French are overlapping means I will have a correct prediction over here, okay? The next word is exit. The next word here is prez, right? So over here, I will have a score of 0. Okay. Now, what is Rouge actually calculating? Rouge 1 is actually calculating the F1 score of the this thing. No. Rouge 1. So when you just calculate Rouge 1, it is going to give you two values. It's going to give you the precision of the predicted word. It's going to give you the recall of the predicted word. Can you guys quickly remind me what precision and recall is? Precision, if you remember, is true positives upon something. What is true positive upon, true positive plus false positive, right? That is my precision. So precision is how well am I able to predict the words correctly, right? That is my precision. So whenever I'm going to compute Rouge 1, along with this Rouge 1, I'm going to have the precision associated with this Rouge 1 score, the recall associated with this Rouge 1 score. Okay. What I can do is I can take the harmonic mean of these two to give me the F1 score, right? Are you guys following what I'm saying? If I take the harmonic mean of these two, I will get my F1 score. Are we in agreement? Okay, perfect. So typically what people do is they will keep the uh, precision and recall associated with this Rouge score separate. Um, so this is one type of root score. If we now increase n, right? So for example, if we increase n, this will basically count how are my bigrams overlapping, right? How are my bigrams overlapping? So my bigrams are basically two words at a time. French exit, French press. Can you guys tell me if I look at French exit and French press, if I compare these two bigrams, are they the same? Yes or no? They're not, right? They're not the same. So this will actually get a score of 0 when I'm calculating. So this is a false, this thing, right? It's a false positive, false negative. Yeah, true negative, sorry. It will be a true negative for for my computation, French exit and French press. But then I'll have some, these things also, right? Okay. So this is how Rouge 1, Rouge 2, Rouge 3, etc. are computed. Now we have something which is known as Rouge L. Okay, Rouge L is the longest common subsequence based statistic. So basically, it will first apply the LCS, longest common. So what it will do is, it will basically come here. It will calculate what is the longest overlapping subsequence between my original and my predicted summary. Based on that, it will select L, it will select an N, and then it will compute the precision and recall over here. So this is based on the longest common subsequence between my predicted and my original summary, and that is how this Rouge L is calculated. So now if we actually go and look at our Rouge precision, Rouge recall, and Rouge F, here Rouge F is nothing but my this thing, right? This is Rouge L score, I believe. So just one moment. Yeah, no. This is the F1 score of these two. So this is nothing but the harmonic mean of these two, right? So if we now look at these give us a more clear picture of how well our model is doing. So for this particular entry, the root score is 0.6. So we can expect these two to be quite similar. Whereas for these really low numbers like 0.2, this thing, essentially there is absolutely no overlapping words between this and this, right? So in general, when we want to evaluate the summarization power of our model, it is better to use the root score rather than the bag of words accuracy that is normally reported during Keras' training. Okay, so that's the takeaway from all this. Cool. Any doubts at this point? Really sorry, took a really long time to finish this topic. Long short-term memory. We will now actually begin with the content for today's lecture, which is named entity recognition. What I will do now is I will pause here for any questions that you may have. If you don't have any questions, we'll take a quick 5-minute break if you guys are okay with it, and we'll start named entity recognition. Uh, what I'm hoping to complete today is at least most of the concepts. If in case it becomes too long, I will skip the code and I will explain the coding part later. Okay, next class. Is that okay with everyone? Okay, perfect. So, any doubts? If you have any doubts, you can ask me now. I would love to take them. Otherwise, what I'm going to do is I'm going to leave this problem statement on the page. I'm also going to start a timer now. Okay. Once we come back from our 5-minute break, we will start talking about named entity recognition. So see you guys in 5 minutes. And we're back. Can I get a quick confirmation if you guys are back? Okay. Awesome. At least six people are back. Nice. Cool. So I'm going to assume at least six people are back and let's proceed. Right? Okay. So, guys, we are now going to start talking about this new problem called named entity recognition. Okay. What is named entity recognition? Very simply put, it is going to look something like this, right? So, for example, over here you have this article on dog bite. Okay, you have history of present illness, past medical history, allergies, medications, all this, right? The job of a named entity recognition system is to retrieve useful information from this article, right? So, for example, here you have this wound which is here. The word wound over here is being detected as a symptom, right? The word pulmonary fibrosis and atrial fibrosis has been, atrial fibrillation. Atrial fibrillation has been labeled as disease over here. Then you have this folic acid, verapamil, Bactrim, omeprazole. Okay, some of these are just impossible to pronounce. You have all of these which are chemicals, and you have dosage over here, right? So extracting pointed information from articles like this is the task that we're going to consider today. Why are we considering this task? Because the state of the art, even today, the state of the art for this task is LSTMs. So the main purpose behind discussing this problem today is, now that we have learned LSTMs really well, can we go and achieve state of the art for something? It turns out that the state of the art for named entity recognition right now is a certain method which uses LSTMs, but it uses LSTMs along with a bunch of other techniques. So let's study this systematically. Let us see what additional things we need to do to an LSTM so that it becomes state of the art. Let us see that. Okay, so that's the objective behind studying this problem today. For us, like for the exact problem that we are trying to solve, we will be given a corpus which basically contains medication and complaints associated with that medication. Okay, our job today is going to be looking at the review that has been given for a certain medication by a user. We're going to use that review to basically extract things like side effects, symptoms, etc. Okay, from that review. That is the purpose of today's problem statement. Are we clear on what the problem statement is? If anyone wants me to repeat or explain this again, please ask me now. Right? Our job is to do this, to get symptoms, diseases, etc. from a certain corpus. So why information extraction, right? To be very frank with you guys, I think this is the problem which will appear the most in an industry, right? Because in an industry, we have a lot of documentation, we have a lot of uh, data which has been generated, but not enough man hours to actually spend gaining insights from that, right? Because people like you and me, we charge a lot of money to do these kinds of things, right? So it becomes kind of expensive. So the whole point of information extraction is to reduce man hours by extracting pointed information. One very extreme use case I can give you is, there's this really interesting startup which is a law firm. Okay, so these guys want NLP researchers to come and extract precedents and things like that from the history of their law firms cases within India. So this is one of those interesting startups that you come across which are really using NLP tools to get their work done. So just wanted to mention that. The whole point of named entity recognition is to um, answer very specific questions. So there are different variants in this, but most commonly we are looking at the nouns which are there in a certain corpus. Of course, this will change depending on the corpus and the type of task, but more often than not, our goal is to organize information, to extract the nouns over there, and then extract some meaning from those nouns, right? So that's the broad goal. So let's take a few more examples. So if you notice, sometimes in your email, like maybe in Gmail, you might have noticed, you could there are times where you say, please find something attached, and then Gmail reminds you, you forgot to attach something, right? So stuff like that. You can have these intelligent systems which look at these messages and they actually automatically suggest you to do something. So over here we have a message which reads, our next meeting will be on Friday, September 18th. So this tool which is available automatically suggests, okay, since you have mentioned it, why don't you schedule it right away so that you don't forget, right? So this is another application of this. Another application could be, using tweets to extract information about your products. Like for example, you have this tweet here, @Chroma Retail. Please train your staff in Chroma Bandra to provide correct details of customer support for Fitbit. The number given doesn't work. So essentially, this lady had a problem with the customer support number for the Fitbit she bought from Chroma Bandra. So you could extract pointed information like which Chroma store, which product, what was the problem. So these things can be recognized with a named entity recognition system, right? So you can extract these pointed bits of information from text corpi like this. Okay, so this is what it looks like. If you guys have understood this problem statement, can you guys tell me what is the major difference between this and parts of speech tagging? What's the major difference between this problem and parts of speech tagging? Yes, very domain specific. POS is just on syntax. Yes, yes. And if you notice, we are somehow dependent on, yeah. POS does not predict, okay, correct. Mostly nouns, yes. Multi-word entity, yes. Right? Multi-word entity, that is kind of a good observation, Indradeep. Here we use semantics, right? Yes. So if you really think about it, right, historically speaking, these two tasks have been very closely knit together, right? I've already given you a lot of hints already that most of the time we are after the nouns in the sentence. So don't you think parts of speech tagging should be like a pre-processing step for us? Do you agree that parts of speech tagging is like a pre-processing for this task? Because we want to hunt for nouns and we want to categorize those nouns on top of detecting them, right? And it may be possible sometimes that what we're detecting is not a single word or a single noun. It is an entire noun phrase, right? So 99 out of 100 times, named entity recognition and parts of speech tagging go hand in hand, okay? In fact, you would want to do something like parts of speech tagging before you feed it into the system. So let's see that. Okay. So based on this intuition, of course, the most classical approach would be to use something which is rule-based, right? And there are multiple ways of coming up with rule-based solutions for named entity recognition. Have you guys done web scraping? You've done web scraping at some point or the other, right? So let us say I ask you to build a program which goes to multiple websites. So if you go to Myntra, for example, right? If you go to Myntra, for example, you will have these product names and prices associated with them, right? I think it will be very easy for you to guys to look at the structure of that web page and write a program which does this for every product page, right? This should be easy. So this is also in some sense named entity recognition, where we are taking advantage of the structure of a web page to extract pointed information from it. But of course, the world is not so nice. They will sometimes write long essays to store information. So we can't always rely on HTML. So the most obvious step, the next logical step is, let us do something which is dictionary based, right? So instead of relying on the structure of an HTML page to give me the information, what I will now do is I will pay somebody who's a domain expert to create a dictionary of words which are most commonly encountered, right? So for example, I can pay a person who is a pharmacist to write down the names of all the medications and to write down all the diseases associated with those medicines. So given now that I'm given a new piece of text, all I have to do is I have to look for that medicine name over here, and then I have to pull out the information associated with the disease and give it to you. That is one very simple approach to solve this problem. What is the basic issue with this? What's the basic limitation over here? What if a new drug comes out tomorrow? What will I do, right? What if, out of vocab is the major issue over here. It takes a lot of time and effort to maintain this dictionary, okay? So dictionary-based solutions aren't great. Cool. So now let us go to rule-based solutions. So first one is, can we apply a big O of 1 algorithm on it? If that is not possible, let us now go and devise some rules. Let us try applying something like a tree-based solution, right? Decision tree-based solution. So rule-based solutions are exactly that. If you guys remember, we had discussed a very heuristic pipeline for POS tagging, right? Do you guys remember that? A very heuristic thing for parts of speech tagging? Okay. So the same idea can be applied here. I can now define some rules for what words are what, right? I can define some rules based on the parts of speech tag, and based on the type of rules that I do, I can essentially extract the information. So let's kind of go through this algorithm here. This is a heuristic pipeline. Let us see what we're doing with it. So I have this text document here now. Let me just zoom out a bit. Yeah. So I have this text document here. I'm going to apply pre-processing on this. I'm going to apply sentence segmentation. I'm going to do chunking, splitting, cleaning, punctuation, all those things that we most commonly do. Once I'm done with this, I'm going to first get all the parts of speech tags associated with this corpus. Once I have the parts of speech tag, I can simply apply a logic, right? If this is a noun, then do something with it. Otherwise, don't do anything with it. So if word in POSIX is any title, if word in POS X plus 1 is noun, right? This basically means I'm now picking a noun and any word which is coming before that noun. Why am I interested in doing this? Because generally in the English language, the word which just comes just before a noun is an adjective, right? It is a word which describes something about the noun. So if I now want to extract phrases which make sense to me, I can take a noun, I can take one or two words before it, and then I can call that whole thing as the entity, right? This is the named entity. Okay. So this is a very heuristic approach to do this. And then you can mark this as name. And then to actually mark the class associated with this name, we go back to our dictionary. Okay. So this is what a rule-based solution will basically look like. Of course, this is not adaptable in the sense that I cannot always use this algorithm for different approaches, right? So for example, if I go to a medical document, most of the words there are going to be Latin because we use Latin words to describe these different types of fungi, bacteria, and disease-causing entities, right? So that is where we'll run into problems if we do something like this. Our parts of speech tagging may not be strong enough to handle that, which is why we have to go for machine learning approaches. The good thing about a machine learning approaches is tomorrow, if some new type of text comes in, like for example, you form a new company, all the documentation associated with that company, you don't have to invest a lot of effort into building that dictionary or rule-based system, right? You can simply apply a machine learning approach which will do everything for you, which is why we would go for a machine learning approach for a task like this. Okay. The typical machine learning approach is this, right? First, I will have documents with annotations. The annotations are nothing but all the named entities in that document. I will prepare a data set out of this. I'll prepare a training data set out of this. I will train my machine learning model. Based on the machine learning model, I'll take some raw documents. I'll annotate them with automatic annotations, right? This is how I will typically solve my problem. The algorithm that you can apply here can be any one of your classification or regression type algorithms, right? Of course, the cons of this are a few. So there are a few cons. The problem of identifying and labeling entities through understanding the context. So the con that we're talking about here is all the cons associated with the methods you've studied so far, right? Contextual information will be missing. So if there is a named entity, so for example, you have this word New York, right? So New York would be split into New and York sometimes, and sometimes it could actually be the city New York. So we wouldn't know which case we're talking about. It could be, you could be talking about a new type of breed, a new breed of dog that you have taken as a pet, right? So York is also a breed of a dog. So my New York puppy could be the phrase. Over there, it's not the city New York, right? So that is the issue that we will have over here if we follow this way of doing things. So of course, we need to use whatever we have learned so far to capture contextual information. What is the best method that we have learned so far to capture contextual information? It is LSTMs. So we're going to apply LSTMs for this. That's the whole discussion. Okay. So cool. So why is this? What makes named entity recognition a hard problem? I just gave you an example, right? Depending on the context, the words appearing together may mean different things. So you have an inherent ambiguity in segmentation, right? Then we have recognition ambiguity. So Nirma, for example, I think all of us are 90s kids. Like most of us are 90s kids. We have all heard this Nirma ka. Okay, some people are not. Okay, some people are older, some people are younger. Both are possible. But have you heard of this Nirma washing powder Nirma ad? Yeah, everyone has heard of that at least, right? Okay, some people have not. Please YouTube it. Please YouTube it right now. It has to be burned in your memory. It's one of those earliest jingles which was very popular. Okay. So if you have not heard of it, please go. Please go and see what washing powder Nirma is. Um, Now, once that ad came out, right, parents started naming their daughters Nirma because of the ad. Like you'll see some 80s, 90s kids whose names, like ladies whose names is Nirma, right? So, so now comes the issue there, right? Now we don't know whether we're talking about the person Nirma or the washing powder Nirma. So you have this ambiguity which comes in due to that, etc. So these kinds of issues are what make named entity recognition hard. So it becomes important to use the context to figure out how these words are appearing there. Okay. Which is why we need LSTMs, which is why LSTMs are in fact the state of the art for this. Right? Okay. Now, let us actually talk about some methods which have worked well before LSTMs came into the picture. Okay. Before LSTMs came into the picture, the method which was most popularly used for this task is that of a linear CRF. Okay, the CRF here stands for a conditional random field. Okay, the math behind the conditional random field is kind of straightforward. In fact, I think you guys only will tell me what this is. Can you guys recognize what this thing is? The right hand side, you have e to the power something by summation of e to the power something. What does this remind you of? Entropy? Softmax. Guys, it should remind you of softmax, right? Correlation I get, sigmoid I get, entropy I also get because yeah, you use softmax when you are training with categorical cross entropy. But the correct answer I was expecting is what Deepit gave me. Okay, this is the softmax operation. P theta of y given x is a softmax. So if you look at it, right, the math of a conditional random field is nothing but a softmax. In fact, the conditional random field that you have here, no, nothing to be sorry about. We all make mistakes, Indradeep. We learn from them. Okay, yeah. So the major math behind the conditional random field is that of a softmax operation. But we're applying the softmax operation kind of carefully here. Okay. So first of all, let us try and understand what is the input on which this method is applied. Anil says even ChatGPT makes mistakes. Yes, that's absolutely true. Even ChatGPT learns through human feedback, right? So we'll also learn through human feedback. Okay. Anyway, coming back, let's talk a little bit about conditional random fields. I want to sort of talk about this first, and yeah, okay. So let's actually go through this. Conditional random fields. Okay, cool. So, okay, Biswarup says he wants to apply for a job to ChatGPT. Okay, that's possible, I guess, if you can clear their interviews. Getting into their research team will be difficult, but getting a job as a prompt engineer or something would be possible, right? Okay. Anyway, uh, yeah, coming back, what we are now discussing is this method called conditional random field. It has been applied as a method to solve this problem before LSTMs came into the picture. The basic idea is this, okay? If you have a sentence like this, I have a fat cat. So if I have a sentence like this, right, where I have these numbers, Along with each of these words in the sentence, I'm going to have an associated hidden state. Okay. So with this, I'm going to have hidden state 1. With this, I'm going to have hidden state 2. With this, I'm going to have hidden state 3. With this, hidden state 4, hidden state 5. Okay. So essentially, for every unique word in your document, okay, we are going to have an associated hidden state. So this is almost like doing one-hot encoding of your input document, but you're only keeping track of the index number. Does this make sense? What I'm saying? You take your sentence, you take the vocabulary. In the vocabulary, you will have a number for each word, right? So what I'm now going to do is I'm going to treat that number as a hidden state. What do I mean by this? Do you guys remember when we were looking at bigrams and trigrams, when we were doing things like when we had applied this method, right? Naive Bayes, when we had applied the naive Bayes classifier for predicting the next word. Do you guys remember what the conditional probability equation looked like? Do you guys remember that? For bigrams, for example, I would basically have to predict the probability of have given I was the previous word, right? This is what we were trying to predict. This is the conditional probability that we were trying to predict. So the next word was given to us based on how high this value was, right? Based on how high this value was. Okay. Now that we have this background, now that we have recollected what naive Bayes was looking like, now let us discuss what this CRF is. Okay. The reason why I'm discussing this in detail is because we're going to use this to improve the performance of our LSTM later on. Okay. It turns out we can do this to improve the performance of our LSTM even further. So let us understand this a little better. So now I have my sentence like this. Okay. Imagine that I have all sentences in my corpus encoded like this. I'm going to have a number associated with each word. And what I'm now going to calculate is basically the probability of this given this, right? If I just do this, then I will have naive Bayes. The difference between naive Bayes and this conditional random field over here is the following. Okay. So let's sort of take this and let's work with this. So just want to explain the difference with naive Bayes. Now the major difference here is this, okay? What I'm trying to build a dictionary for, right, is the probability of the hidden state given X. Okay. Now I'm no longer having word over here. So in naive Bayes, right, guys, I have one word over here, I have one word over here. Okay. But when it comes to conditional random fields, I don't have words over here. I have the associated hidden state with it. So every word has an associated hidden state with it. I'm now given a word, I'm going to try and predict the next hidden state. I'm not going to try and predict the word directly over here. I'm going to try and predict the next hidden state given this. So from I have a probability which goes to the hidden state associated with this have. I have a probability of going to the hidden state associated with this fat and so on. Okay. So that is one extra layer of computation that I'm putting here. What is the extra layer? Instead of predicting the word directly, I'm going to predict the hidden state, and then I'm going to capture relationships between the hidden states to do everything. Okay. What is that relationship? Let us see. So for that, we'll have to pay a little bit of attention as to what is inside this exponential. Okay. So inside this exponential, if you notice, I have this Wj, which is nothing but a weight term, and I have this Fj. This Fj is a function which takes a word and a hidden state as input. This becomes important, guys. My Fj is now going to take a word and a hidden state as input. The basic, so this Fj function is known as my feature. Okay, this is known as a feature. My feature is itself now a sum. Okay, it is a sum over the entire sentence. Okay, the L over here is actually the sentence length. Okay, the sum over here is a sentence length. What I'm doing to calculate my probability over here is I'm taking these features, I'm taking one sentence at a time. I'm looking at the words which are there in the sentence. The words are these X numbers. I'm looking at these hidden states now. Okay, yi and yi minus 1 is nothing but the hidden state of this word and the hidden state of the previous word. Okay, and I have the index, which is the position in which this word is coming in that sentence. Okay, so now my feature over here is a sum of these individual functions which are just looking at bigrams. So do you notice that these are bigrams? Yi and yi minus 1, these are bigrams on the hidden states over here. Okay. So what this is essentially doing is it's taking a function of every bigram which is possible in my sentence. It is applying that function and it is summing over all of that. The sum over the entire sentence is what I define as my fj, which is my feature. And that is what is coming and sitting in the numerator of this. In the denominator, if you notice, I'm going to replace the y over here with otherwise. So what I'm changing in the denominator is I'm essentially summing over all possible hidden states. So what one term in my numerator is going to give me is the probability of a hidden state given a word. In the denominator, I'm going to sum over all the hidden states possible. So this all the hidden states possible is what I'm going to sum over, and the relative probability is what I'm going to store over here. Okay. So what do I essentially now have to do to get the prediction for the next word from this kind of a model? What I'll have to do is I'll have to look at the y. So given a word, I'm not predicting a word. I'm essentially predicting something like the this thing. I'm predicting something like the tag, the named entity tag associated with this word. So for example, if this is cat, this y will have to be animal, right? That is the major difference here. So this is what conditional random fields look like. And if you're wondering what these fjs are, right? These fjs are usually binary. These are binary decision kinds of functions. They will either return a true or a false. So this could be something like is noun, is pronoun, is adjective, things like that. So these small functions that you see here, right, which are applying over the entire sentence, these are going to be nothing but true false statements. And this is what's going to give me my conditional random field here. Okay. This is kind of the math behind conditional random fields. It's kind of optional, but I just wanted to go through it since the equation looks kind of simple. So, okay. So I'm going to pause here and let us see. Indradeep's question is, so I have j such features in the numerator? Yes. You have j such features in the numerator. So you have, okay. So I'll give you an example, Indradeep. If I just took, let me say f1 is the function is noun. So now what I'm going to do to get p theta of y is I'm going to, so let us say I have just one feature, which is noun. So what's going to happen now is it's going to go and it's going to apply is noun to every combination that I have, right? So it's going to look at the hidden state, it's going to look at the word, and it's going to apply the is noun function on all of them. Once I've applied it to my entire sentence, what I will get is the number of nouns that I have in this sentence, right? So my fj over here will become the number of nouns over here. So just like that, we can design multiple binary features and we can put it over here. Okay. And today what we're going to see is it is possible for us to use a neural network to define this. I can now define this fj as w transpose t plus b, right? This is, so all I have to do is I have to put these things in a vector. I have to multiply it by a weight matrix and a bias. If I now do this, I can essentially build something which is known as a CRF layer in my neural network. So today what we're going to see is if we take an LSTM and we apply the CRF on top of it, we could improve the performance of our LSTMs. That is one major reason why we're discussing this right now. Okay, cool. So let's move on. Essentially, the math of this is sort of defined here. I'll leave it to you guys to sort of read this if you want more details. There are also some nice examples over here. So you have these kinds of examples and you can take a look at that and understand this concept a bit better. But now we'll actually come to the deep learning part of this discussion. That is, what do we now do to build an LSTM which can achieve the state of the art? If we just use LSTMs as they are, we probably won't get state of the art. it becomes important to make some changes to this LSTM architecture, and let us now discuss those. Okay. So the state of the art is achieved through something which is known as a hybrid method. Okay. So we saw what rule-based methods were. We saw what CRFs are. We already have studied what bidirectional LSTMs are. Can you guys quickly remind me what is the use case for a bidirectional RNN? First, let's talk about bidirectional RNN, then we'll go to bidirectional LSTM. Bidirectional RNN. Let's recap this concept really quick. Okay. Fill in the blanks, right? So the main concept between the main idea behind a bidirectional RNN is we have one hidden state for start to end and one hidden state for end to start. So my dash elephant took all the bananas I had in my hand. So if we had to do a fill in the blanks over here, I would have to tell my neural network what is the context in the forward direction as well as what is the context in the backward direction, right? Only when it looks at all the data in the forward as well as backward direction, it will know that it has to put an adjective over here, right? So if it is able to process it from both directions, it will realize that, okay, what is expected here is an adjective. What should the adjective be describing here in this sentence? What? Come on, guys. What's the adjective? Yeah, it should be describing my elephant, right? So I can do this only if I have one hidden state which is capturing everything which is coming in the forward direction, one hidden state which is coming in the backward direction. The same idea can be applied for an LSTM, right? So just like we had stacking LSTMs where we put the output of one into the other, in the case of a bidirectional LSTM, we don't stack them. What we do is we will have one thing where we present the output from front to back, another where we're presenting it from back to front, and a combination of these two outputs is what we will use for our final task. So there is actually going to be no relationship between the forward LSTM and the backward LSTM, right? So let's see this now. So an architecture for a bidirectional LSTM with a CNN essentially looks like this. So now for some time, let us just look at this architecture and let's figure out what's happening here. Okay. So here we have this sentence. In fact, let me get it here. It will be easier for me to talk about this if I take it to my notebook. Right? Okay. So let's study this architecture for a while. So my architecture basically looks like this, guys. I have a sentence here, which is we saw paintings of Picasso. Okay, this is my sentence. Do we know how to get this part? Does everyone feel confident we can get this? This is nothing but word to vec or embedding layers, right? From Keras, we know how to get this. Additional word features are basically things like POS tagging, right? What else can you associate with a word? So for every word, you can give a parts of speech tag. You can give something like, is it a rare word or something like that. So basically word features like is noun, is rare, etc. Right? Things like that. Different word features. Now, yeah, plurality or singularity. Yes, that. Yeah, that plurality. Okay, it's plurality, not plural. Okay, sorry, tongue twister. I'm just going to ignore this. So we're pretty clear on how to get word embeddings and additional word features, right? Now, here comes the interesting part, okay? Here comes the interesting part. we have this new thing sitting here now, which is known as CNN extracted char features. So what is this? Okay, what is this? So CNN extracted char features are essentially a special type of CNN trained to predict the next character in a list. Okay. So CNN extracted char features are basically, so essentially what they do is they take a CNN whose job is to predict the next character. So what we were doing at a word level one class back, right? They train the CNN to do this at the character level. So character by character, the CNN will try to predict the next one. And one of the layers of that is what we call the CNN extracted char features. So why do we need this, first of all? Because words at a word level, right? We may not have enough information to predict what should the next character be, right? Things like what Arun just mentioned, plural versus singular, or things like parts of speech. So should it be eats or eaten or should eat, something like that, right? So to capture things like that, we need character level information rather than word level information, because word level information can have, you can have different words of different forms, right? Generally, when we do stemming or lemmatization, we try to put all of those things together. But the advantage of a character level, the advantage of character level information is we can get access to different forms of the word over here. So the major reason why people include this also in our word embedding is to capture the different forms of a word. And this is why we sort of apply this method to append things to our word embedding, right? Okay. So Indradeep's question is, we need a matrix for using CNN convolution, right? So for CNN, do we create embeddings for each character of a word? Hold on, I'll quickly explain that. The way this usually works is as follows, okay? So what we're now going to have is, so for at least for this NER architecture, right? The NER architecture which achieves state of the art, this is how it works. You will take this word Picasso, you will pad it before and after because you want to make sure all words are of the same length. So we will apply padding till we get the max length of our words. Okay. Why do we need to do this again? Same reason as in LSTMs, right? Same reason as in LSTMs, because we want to make sure short words are not unnecessarily given more importance than long words. Same reason we apply this padding. Once we apply this padding, we will have this character level embedding. What is this character level embedding? It will basically be a one-hot encoded label, one-hot encoded vector, which tells us which character is there in that position. Okay. Additional char features are like, is it capital or small? Is it a number? Is it alphanumeric? Is it a, what do you say? Vowel, or is it a what do you say, special character, things like that, right? We have these kinds of features here. Now this is what we pass a convolution operation on. Once we have these kinds of encoded vectors, we apply a 1D convolution here, guys. We don't apply a 2D convolution, we apply a 1D convolution to this. The output of the convolution is fed to a dense layer, and then the output of this dense layer is basically interpreted as a prediction for the next character. Now, once we train that network to predict the next character, we will extract just the last layer of this dense network, and we will use this as the CNN extracted char features over here. Okay. So are we clear on how we are getting the CNN extracted char features? Are we clear on that? Okay. Are we clear on why we are doing it? We're doing it because we want to capture the different forms of a word. This is not possible through everything we've studied so far, by the way. Word embeddings will not really account for this because we apply stemming lemmatization. Additional word features will only tell you word level information. This CNN character, this thing will give us forms of a word kind of information. Okay. Now comes the interesting part. Now, once we have this kind of an input, right? Once we take every word in our corpus, we convert it into word embeddings, additional word features, CNN extracted features. this is what we pass to an LSTM. Okay, this is what we pass to an LSTM. So because now what we have is a bidirectional LSTM, we will have one for forward, one for backward, right? So now let us see how these words are being passed. Okay, so first let's understand the forward LSTM. So we saw paintings of Picasso are going to go in order, right? These are going to go in the front direction. But if you notice, the zero for the backward LSTM is starting here. Okay, for this backward LSTM, Picasso will come and sit here first, then off will come, then paintings will come, then saw will come, and then we will come, right? So this is how we're essentially passing information to our backward and forward LSTMs. Are these LSTMs connected in any way right now? Are these LSTMs connected in any way right now? No, right? Yes. This is intentional, by the way. We are not going to connect our LSTMs until we come to the final stage. So let's see. So from this LSTM, I'm going to get one sequence of outputs. From this LSTM also, I'm going to get one sequence of outputs. Now, this is the interesting thing, okay? The output that I get from the forward LSTM for V is concatenated with the output I'm getting for the backward LSTM for V. Okay, this is how the architecture is. Okay, whatever my forward LSTM is giving for V, I'm going to concatenate with whatever my backward LSTM is going to give for V. Do you see that this will have just one word processing, whereas this will have 5 words worth of information over here? Do you see this? This is why it's done. Okay, this is why it's done. So the structure of our output layer looks like this. We're going to combine the LSTM outputs for that word. We're going to then generate something which is known as a tag score. Okay, so this is done simply by applying a dense layer over here. Okay, so we simply apply dense layers in each of these places. And finally, we are going to get a vector. This vector is going to be interpreted as a tag, right? So we have different tags. We'll quickly go and see what those different tags are. But essentially, it will look like this. So V becomes O. So whenever we have an O over here, it means that it is none of the above. Okay, it's none of the above. But if you look at Picasso, this is S per, right? This S per over here stands for tag of a person. Okay, so this is how we're going to get the output from our network. So broadly speaking, a bidirectional LSTM with a CNN architecture looks something like this. Okay, this is what the architecture looks like. This is what the CNN architecture looks like. Now let's discuss what is the CRF extra thing over here, right? So the extra CRF thing over here is this. Indradeep's question to me, so ultimately it's a multi-class classification. Yes, Indradeep, it is a multi-class classification, but we are not applying multi-class classification because of the problems we saw here, right? We're not simply going to use what we know about multi-class classification. We're going to put some thought into building our architecture because we want to maintain different types of information in our representations. So that is the additional on top of multi-class, right? Okay. So that's the idea. Actually, guys, we are out of time. And I think that if I start discussing how CRF is applied to this, it will get too long. So let us do one thing. Let us sort of discuss everything from this point on next class. Next class, we're also going to be studying attention. If required, I will schedule an extra class before we come to the transformers part, right? Because learning attention is important. So if required, I'll schedule an extra class if it's required. Is that okay with you guys? If I have to schedule an extra class to cover this content? Okay, awesome. Because I don't want to complicate this. If I now explain this, right, we'll lose track. So next time what we'll do is we'll come back, we'll revise this architecture, and we will see how we'll apply CRF on top of this to get our job done. Because it's the combination of these concepts which gives us the best possible performance, right? If you guys are wondering what is the task I'm talking about, I will give you access to this paper. The name of the paper is Stanza Python paper. If you guys are interested, you can sort of take a look at this. This one. You can sort of take a look at this paper. It is essentially a paper which has the current state of the art for named entity recognition. So a lot of doctors and medical professionals actually use this to make it easier for themselves to identify new medication. Okay, it's a very helpful library. I just want to, yeah. Stanza is from Stanford, yes. So what we're essentially studying is how these guys got the best performance models for their NERs. So if you notice here, this is the current state of the art. It even beats BERT-based algorithms in some cases. So I just wanted to show you that result. It's very interesting actually. I was going through this paper and I saw that it was beating BERT. Sorry, this is not the paper. Just 1 minute. So just give me 1 second. I found this paper here somewhere. Okay, tell you what, I'll share the paper with you next time. Yeah, what I'm going to do now is I'm going to start the doubt session. Those of you who don't have doubts can leave, and I'll quickly handle the doubts that were asked in this class. Okay, so I see just 2 questions now. Let me answer Arun's question first. Sure. So extension for the business case, since it was released late for us, I will communicate this. I will make sure that you get enough extra time. How much was the delay, by the way? Was it 4 days or 5 days? Like, can you give me the number of days, like after which it started working? That way I can ask for a appropriate thing, right? So, do you guys remember how many days it took for us to fix the issue? Or do you guys just want a 1 week extension? Can you guys help me with the number of days you want the extension for? 4 to 5 days? Okay. So something like next Monday, I'll try for that. I'll try for next Monday. Sure. Cool. I'll try my best for that. Next weekend. Uh, okay, I'll put the request through. I don't think they'll entertain 1 weekend this thing. They'll at max go for the number of days which we need to compensate. I'll put that. 13th is the current deadline, right? 13th is coming Saturday. I'll try to make it fine. I'll try my best to make it 20th, but I think reasonably you can expect 18th as the deadline. So I'll try my best though. Cool. Now let me answer Ravi's question. In the last class, the output of the model was not really great. The summary made sense, but the information was incorrect. Do we know why? Yes, we actually do know why. So like I said, like Ravi, whatever notebooks we create, right? The constraint that we're given is it should run on Google Colab's free version. So some of the optimizations we did was we kept only one decoder layer. We took 3 encoder layers but one decoder layer, right? It would probably be more efficient if I had 3 decoder layers where each decoder layer is getting the encoder layer from the hidden state from each of those, right? That kind of an architecture would be more efficient, but we were not able to do it because of the memory restrictions here. So one way to improve this would be to increase the number of layers in um, the decoder, right? So that it can use more contextual information to give you answers. The other strategies which are recommended are adding attention layers or using transformer-based architectures for this. So next class, we'll see why this is effective, right? Another thing we could do is we can change different hyperparameters. So we just went for the simplest optimization stack. We didn't really mess around with hyperparameters. Whatever output you saw here was with just one pass, right? So yeah, all of these methods you can try. What I will suggest to try first is increasing the stacks in your decoder architecture. Like that I think will help the most. But again, I've not actually tried this, so can't say. But if you see something, right? If you try something and you improve it, please share it with the class. It will be really nice if you can share it with the class. Cool. Any other questions? I'll just pause for some more questions. Otherwise, we can all head to Ravi's video. Like, I think Ravi will send us hot chocolate, or at least he'll send us a photo of hot chocolate. We can see that and feel happy. Mm, cool. Okay. Was today's lecture too heavy because of the number of concepts? Did you guys feel like today's lecture was heavier? Okay. Yeah, I think the reason being this, right? I started off with GRU's math. So I think this part became heavy. And then when we came to CRF math, it became even more complicated. So yeah, mm, sorry about that. But okay. What I will encourage you guys is maybe just check out this notebook today, right? Which I'm going to be attaching. This one, named entity recognition. If you guys have any doubts about CRF over here, you can reach out to me. And yeah, we can, or if you want, I can repeat this a little bit next class if it makes it more convenient. GRU felt very confusing, so many connections. Yeah. So here is the real issue. Okay, Indradeep, I'll show you what the issue is. When a paper comes out, right, what people try to do is they'll try to make small changes and they'll show improvements. Okay, that makes the definition of a GRU very vague. So if you go to Wikipedia, right, gated recurrent unit wiki, you will see that even this has so many variants. So you have a fully gated unit where your equations are this. Then you have this minimal gated unit which has this kinds of equations. Then you have type 1, type 2, type 3 inside this itself, right? So there are actually many different interpretations for the same diagram over here. The different interpretations depend on, are you going to put a matrix to multiply over here or not, right? So when we decide to put a matrix over here, we get this type fully gated recurrent unit. If we decide to not put this matrix here, we will get this type 3, which is essentially just going to be the sigmoid of a bias, right? So that is why this kind of gets confusing. And but these equations are totally wrong. Like, they're totally wrong, because if you notice here, ht tilde should have 1 minus, should have zt element wise multiplied with this, right? That's not happening over here. So these equations are totally wrong, for sure. So yeah, this was the correct one. These are the correct equations. So different variants just depend on arbitrarily removing or adding these matrices or biases. So for example, type 1 is both. Type 2 is just the matrix multiplication. Type 3 is just the bias. And yeah. And then you have this minimal gated unit where you even get rid of this part. Essentially, you get rid of this part. You essentially just have a single forget gate. You have this ft which is multiplied here, right? So you don't have this zt separate. Yeah, you don't have this zt separate. Whatever you're using for the forget operation here, rt, that only you're using over here. So yeah, that's your minimal gated unit. Where to use GRU instead of LSTM practically? When you have lesser memory available than an LSTM. LSTM will require 4 matrices. The default LSTM will require 4 matrices. The default GRU will require 3 matrices. The default one does not have these URs. So wherever you see UZ, just imagine there's an identity matrix sitting there. So the reason why people use GRU is because it's memory efficient. Memory and time efficient, actually. So if you have to deploy to a mobile phone or something like that, you could consider using this. It won't cause so much difference also, actually speaking, because my GRU is a single set of matrices, right? Where will this really cause issues for me? Memory is a weak argument. There's just like one matrix difference here. What other reasons are there? Yeah. Yeah, that's what, man. Like, see, maybe if data is less than LSTM overfits, yeah. That's a good answer. But even Wikipedia is telling us GRUs show that gating is indeed helpful in general. Bengio's team concluding that no concrete conclusion on which of these was better. So LSTMs and GRUs are both comparable in performance. This paper shows in detail why this is the case. So I'll just see if I can take you to the results. No, it's not here. It's in the text of this. They've not given any tables here, but I'll just take you to the part. Huh. Yeah. So this section talks about this section 5 in general, right? Talks about which is better. So this is what you could come to and read. It tells you that they're comparable in performance. So there's no real reason to prefer one over the other. Just use whatever comes your way, I suppose. Yeah. But I like your reason. Like if there is an overfitting happening genuinely, because you have a small data set, that is where it will come in, right? I'm pretty sure this paper did not consider the size of the corpus for these tasks. I think it just went with whatever was available. So if you have a small corpus, right, it would make sense to use a GRU instead of an LSTM. Yeah, that's a good reason to do it. But honestly, like, don't use any of these. Just use BERT or transformer-based models, attention-based models. They work much better. Like, it's an order of magnitude difference. So it's preferable to do that in practical cases. Cool. So if there are no further doubts, I'll end the class here today. Thank you so much for your attention. If you do have any doubts, don't forget you can reach out to me on Slack, and I'll see you guys next time. Good night.